Now what we're going to do is extend what we know about circles into an eccentric circle known as an ellipse. Now the ellipse definition is a little bit different from what we've seen before. It still deals with a set of all points with a common distance, but the way we calculate that distance is that the sum of the distance is constant compared to two fixed points called foci, which is the plural of focus. And so an ellipse has two foci that if we look at the distance from any point, so we have a point here on our ellipse, the distance from this point to one foci and that point to the other foci is always the same as if we add up the distances between any point and again those two foci. So the sum of those distances will always be the same. Like with our circle, we have a center value. And the center is denoted the same way as with the circle with the value of h and k. Now notice here we have two different equations here, h and k. We'll go into more detail about this, but the two different versions of the formula are very similar, and really the only difference is these denominators a and b. And the way that I have them labeled is a little bit arbitrary, and as we look at more equations it'll become more clear. But what these denominators tell us is whether our ellipse is wider on the horizontal axis or wider on the vertical axis. And so this first equation here, as long as if we assume that a is our largest value, then we know that this is going to be wider on the horizontal axis because we're looking at the x squared term, which is our horizontal movement. And so this gives us an ellipse that's wider horizontally. However, if our largest denominator is underneath the y term, then it means that our ellipse is elongated on the vertical axis, and it's going to be longer going through the y-axis rather than the x. Now, how do we classify these other new values of a and b? Well, a refers to the distance from the center to the furthest edge, and we call this a semi-major axis, and so we have that labeled over here. And so on the ellipse, let's draw a clean ellipse over here, from the center to the furthest edge, that's the value for a. Semi-major axis. If we go from furthest edge to furthest edge passing through the center, we call that the major axis. Major as in the largest. And going from the center to the edge, well, that's part of the major axis, so we call it the semi-major axis. So when we have the value of a, we can find how wide the ellipse is by multiplying the value of a by 2, and that gives us the full length of the major axis. If I know the value of, or how wide the parabola is, or I'm sorry, how wide the ellipse is, I can find the length of the semi-major axis by dividing the length by 2. Next, we're going to look at the value of b. What does b mean? Well, b is going to be the semi-minor axis. And so from the center to the shortest edge, that's going to be our value for b, and that is our semi-minor axis, minor as in smallest. And then, of course, 2b would be the full length across on the short edge. And so those are going to be the values that we have in our denominator squared. And then again, if we're dealing with a vertical axis ellipse that's elongated vertically, the semi-minor is going to be on the x-axis, while the semi-major is going to be on the vertical axis. And then, well, now we have to wonder, well, what is this value that we have for c over here? Well, c gives us the distance from the center to the focus on either direction. Okay, c for focus. We can remember that. Now, how we find c, it has a very special relationship. We call it a Pythagorean relationship. It's not the Pythagorean theorem because you'll notice it's slightly different. Instead of a squared plus b squared equals c squared, instead of that, it is b squared plus c squared equals a squared. And so the length of the semi-major, semi-minor, the length of the semi-minor axis squared plus the length from the distance to the focus squared will equal the length to the semi-major. And we can kind of remember that because this has to be the longest distance. If we look visually at our ellipse, the distance from the center to the vertex, that distance has to be the longest, and so the Pythagorean relation has to hold through. So what we can do is, once we kind of understand our formula, we can identify the features of our ellipse. And what we're going to do is we're going to look at finding the center, the vertices, and the foci of each ellipse. Now, like with our previous problems, we were given equations in general form, and this does not look like either of these. And so we have to do the process of completing the square. Now, as we go through each of our conic sections, the process of completing the square is going to get slightly more involved and complicated, but it builds on each other from the previous examples. So the first thing we want to do is kind of look at the way that our equation is structured. And this one's a little bit easier because, as we noticed, there's really no constants here. And so the easiest thing to do is, once we just have a single term squared for x and y, we've already completed the square on x and y. There's not really any more completing the square that needs to be done. But notice a key difference between this equation and this equation is that our example equation is set equal to 1. And then we have some fractions over here. And so that's a major difference, and we have to think, oh, how can I take this equation and get it to look like one of these equations? Well, the easiest thing to do is look at the constant and say, well, this has to be 1. How do I get a 400 to become 1? Well, I divide by 400. So we divide everything by 400, and then we go ahead and we simplify the equation that we have. So the 400 divided by 400 equals 1. Now, when we take 225 divided by 400, that simplifies into 1 over 16. And 16 divided by 400 reduces into 1 over 25. And so now we have this equation in standard form. X squared over 25 plus y squared over 16 equals 1. And we can compare that to one of our formulas. Now, to figure out which formula we use, either the one on the left or the one on the right, we want to see which denominator is larger. 25 is our largest denominator under the x squared, so we are going to use this one where a squared is under the x squared. So we compare it, x minus h squared over a squared plus y minus k squared over b squared equals 1. Now notice this part's very, very similar to our circle equation. We're just adding in these values of a and b, and instead of radius, it's set equal to 1. So we're just adding a new layer to our circle because that's essentially what an ellipse is an elongated or an eccentric circle. And so we can identify our center. And just like with our previous conic sections, that starting value is located using the points h and k. So here, h and k in our equation, well, there's no constant being added or subtracted to x or y, which means that h and k are 0, 0. So we have an ellipse that starts at the origin. Then the next thing we want to do is we want to find the vertices. Now, the vertices of our ellipse are these endpoints of our axes, the major axis and the minor axis. So on the major axis, we call them just vertices. Sometimes other books will refer to the smaller vertices on the minor axis as co-vertices. Sometimes they just refer to all of them as vertices. It just kind of depends. So we're just going to find all of the vertices. So we go back to our diagram and see, okay, well, our vertices are the distance from center using the a value, and our co-vertices are center using the b value. And so we need to find a and b. Well, looking at our equations for our vertices, and we'll specify on the major axis, our vertices on the major axis, since a squared equals 25, that means that a is 5. So our vertices are 5 units away from our center. Well, now what we have to do is we'll know, okay, well, 5 units in what direction? So we consider the shape of the ellipse. Since the denominator is largest under the x term, we know that it is a horizontal axis ellipse. And so we sketch a little ellipse here. And it's going to be wider on the horizontal axis. If our center is at 0, 0, we know that our a value is going to extend right and left, a units. And since a equals 5, 5 units to the left and to the right are the points 5, 0 and negative 5, 0. So we have our vertices on the major axis as negative 5, 0 and 5, 0. Now we'll go ahead and find our vertices on the minor axis. Again, similar process, but instead of using a, we use b. Well, b squared is our other denominator, 16. And so b squared is 16, b has to be 4. So that means our co-vertices are 4 units above and 4 units below our center. That means going 4 units up, we have the point 0, 4, and 4 units down, we have the point 0, negative 4. Last thing to find is our foci. So our foci are found by finding the distance from center to these points using the c value. Well, the c value isn't given in the equation, but again, there is this Pythagorean relationship. So we know that b squared plus c squared equals a squared. And b squared and a squared are given in our equation. B squared is 16, a squared is 25, so if we subtract, c squared equals 9, and c equals 3. So our foci, again, are going to be 3 units away from the center. But in which direction? Always on the major axis. So we go 3 units to the right to get the point 3, 0, and 3 units to the left to get the point negative 3, 0. So our foci are negative 3, 0, and 3, 0. And so now we've identified all the key features requested. The center at 0, 0. The vertices on the major axis were 5 units left and right of center. The vertices on the minor axis were 4 units above and below center. And the foci were 3 units left and right of center. And that's the general process for trying to find all of those features regardless of where our ellipse is centered and what it is. We want to start with where is the center and what direction does the major axis run so that we can properly identify the major and minor vertices as well as the foci. Now this general form looks a lot like some of the previous ones that we've seen with many more terms as well as constants. So we're going to have to do the full process of completing the square. And of course, like before, because we are dealing with a more complex conic section, the process will be a little bit more involved. But the idea remains the same with how we've been completing the square so far. So we're going to start by grouping our like variables. 25x squared plus 100x. And we're going to need a box. And then we'll group our y variables. Plus 4y squared minus 40y with another box. And we can go ahead and move the 100 to the other side. And we're going to add a box for each of the ones we have on the left. Now this time you'll notice that we have leading coefficients. And we can't leave those there when we're completing the square. It's going to make our life a little bit more complicated if we do. So we're going to factor out our leading coefficients. But we're going to factor it within each set. And so I'm going to factor 25 out of my x terms, including that x box, leaving me with x squared plus 4x plus whatever ends up going in this box. Now because I factored out a 25, Over here, I need to remember to multiply this box by 25. We'll do the same thing with the y. We'll keep the plus, and we're factoring out a 4. So we have y squared minus 10y plus, again, whatever ends up going in this box. And all of this is set equal to 100 plus, now we're going to do 25 times this box, and we have to remember to multiply the next box by the 4 that was factored out as well. Now we can go ahead and complete the square. B divided by 2 squared means we put 4 in both of these green boxes. And then 10 divided by 2 squared means we put 25 in both of these red boxes. And now we can factor and simplify. So we're left with 25 times x plus 2 squared. And then we have 4 y minus 5 squared equals, and we go ahead and simplify all the right side. I forgot to make this a negative 100, which would have been a bad mistake. We go ahead and simplify the right side. Negative 100 plus 100 plus 100 equals 100. Now that was a nice little coincidence. It doesn't always happen like that, but it just worked out that we end up with a nice little perfect square. So our last step is we need to take it into the fraction form. Our denominator needs to be 1. So, or I'm sorry, not our denominator, our constant. So to get the constant to equal 1, we divide everything by the constant, 100. So our left side will simplify to x plus 2 squared over 4 plus y minus 5 squared over 25 equals 1. So we want to go ahead and figure out the direction of the major axis. So we look at the denominators. Since 25 is the largest denominator, then that's going to be our major axis. Our major axis is going to be on the y, in the y direction. So if we draw a little sketch of our ellipse, it's going to run vertically with our center and then our major axis running up and down. Well, let's look at our equation and identify our center. So the x value of our center is at negative 2, and the y value is at positive 5. So negative 2, 5 is where our center is located. Just like with our previous conic sections, that's going to be pretty much the easiest part. Remember, the x value is always going to be located with x, and the y value is always going to be located with y. There's never going to be a trick there. Just remember your sign switch. So we have our center at negative 2, 5. Now we want to find our vertices. So let's think about our vertices now. For the vertices on the major axis, we need our a value. The a value is always the square root of the larger denominator. And since 25 is our largest, that makes a squared 25, and that makes a equal to 5. So we look at our ellipse and we say, okay, well, along the major axis, our vertice is going to be 5 units above and below. 5 units up, 5 units down. So we take our original point and we're changing the y value. So our center, we're going to go 5 units up from our center, and we're going to go 5 units down from our center. That gives us 2, 10, and negative 2, 0 for the location of our major axis vertices. Minor axis vertices, we're going to go ahead and take the b value. So since 25 was our a squared, that means that b squared is 4. And so we're going to go ahead and say that b is 2, which means our minor axis vertices will be 2 units to the left and 2 units to the right of our center. That changes the x value. So we're going to add 2 to the x value and subtract 2 from the x value. So our vertices on the minor axis will be 0, 5, that's 2 units to the right, and negative 4, 5, that's 2 units to the left. Lastly, we need our foci. So again, we need the value of c. So we'll use our Pythagorean relation, that b squared plus c squared equals a squared. But we've been given b squared, we're solving for c squared, and we have a squared. So c squared equals 21. Well, 21 is not a perfect square, so c just is the square root of 21. It's an approximate value. And if we're trying to graph, we can get an approximate location, the square root of 21 being close to 4.6. But as far as writing our ordered pairs go, unless we're told to round, we're going to use the exact value. So our foci, we have to consider what direction are they? The same direction as the major axis. And so since our major axis is vertical, our foci is going to be above and below our center. So to get our ordered pairs, that's changing the y value. So we start with our center, and we're going to add our value for c, and we're going to take our center and subtract our value for c from the y value. Now, since those aren't like terms and it's going to be an irrational number, that is the exact location. So if it says nothing about rounding, if we need an exact location, then these are the ordered pairs that we put in for the location of the foci. If we want to approximate the locations, then what we can do is use the rounded value for the square root of 21 and add that and subtract that from 5. So we could take 2 and then 5 plus 4.6, and we could take negative 2 with 5 minus 4.6, and we would get approximate locations of negative 2 comma 9.6 and negative 2 0.4. And so that would give us the approximate locations of our foci. And there's all of our features. Our center was located at negative 2, 5. Our major axis vertices were 5 units above and below, while our minor axis vertices were 2 units left and right. Our foci was the square root of 21 units above and below, or approximately 4.6 units above and below our center.